Can you all see my screen?
Yes, sir.
Yes, sir.
Yes, sir, we can see.
Yes, sir.
Okay. I'm already recording the lecture, so you don't need to record that again. Okay. So in the last class, we were discussing about buck converter. So for buck converter, what we did, we had a voltage source and then we had a switch. Suppose this is my VS, that is my switch T1. Then what we are doing here, so we connected a load and the voltage across the load was V0. And
Sir, are you writing something?
yeah, can you not see that?
Yes,
Sir, we
sir.
can see.
Sir, we can see.
Anybody can see?
Yes, sir.
Yes, sir.
Sir, we can see.
Okay. So what is happening here is that whenever, suppose we are making sure that we have a voltage source like this. So suppose this is my VS, which is input voltage, and suppose the voltage across T1. So let me just draw these things in a better way. So suppose we want to show you the pulses. So suppose we are considering the waveform for that pulses. So whenever there is a pulse, the switch will be on, and after some period, there will be no pulses. So the switch will be off, and then again, we are giving pulses like this, and then it will be off for this type of period. So we are just considering 2 pulses period. That is my VT1. So what will happen if we draw the waveform of the output? So if you want to draw the waveform V0, so whenever the pulses is on, we give pulses to the switch is on, meaning all the input voltage that would appear across the output, right? So we will get output similar to input. So this is my input, suppose this is my VS, and then there is no pulse, then the switch will be off, and then whenever the switch is off, the entire input voltage, it will appear across the switch, meaning there will be no voltage at the output. So from here to here, there will be no output voltage, and when the switch is on again, from this starting of this pulse to end of this pulse, then you will again see the voltage. So your output wave shape will look like this. So that will happen. So instead of this switch, actually, if you think of a practical switch, so what we can do, we can just introduce a transistor here. So it will be a simple transistor here, and this is my voltage. So it can be considered as base to emitter voltage. Suppose this is my base to emitter voltage. We are giving these pulses like that. So we have already considered that situation before, and then I am just recapping everything. I will say that same thing for 10 to 15 minutes so that you can recap what we did in our previous classes, and then I will try to incorporate the new topic and new concept that we are going to use for later purpose. So as you can see, our output voltage, it is not purely DC, it is a pulsating one. So what we did in order to avoid this situation, what we did, instead of this switch connected directly to the load, what we did, we just introduce a low pass filter here. So we just introduce a low pass filter. So we introduced a inductor, and then we used a capacitor, and then the capacitor is connected to the load. So this is my R, this is my V naught. So this section actually, this section will form a low pass filter. So what will happen to the low pass filter? If you tune the low pass filter, so based on our switching frequency, what will happen? We know the frequency of the low pass filter is what? 1 over LC, right? So based on the value of L and C, you can easily choose the frequency for which you are going to allow the output voltage or current to pass to the load, or the frequency component that you are going to suppress through the filter. So if you properly tune this filter in such a way that only the DC component is passing to the output, then in the output section, actually, in an idealistic case, what you will find in an idealistic case, you will find that your output voltage is exactly the same as the V average value of this waveform. We have already discussed that in the class, right? Can you remember this?
Yes, sir. Yes, sir.
So this thing, the circuit that we have discussed so far, it is nothing but a buck converter. But with only one thing that we need to introduce here is a diode in this direction. Why is that? Because for the buck converter, what we did, for the buck converter, we have two modes. So in mode 1, so if I consider mode 1, so in mode 1, my transistor T1 that we are considering, T1 is on. So whenever T1 is on, then the circuit would look like this. It will work like a simple switch, and then we'll have an inductor there, and then we'll have a capacitor, and then it would be connected to the load. That is my plus minus V naught R. And since we have a diode here, so as you can see, this is my Vs. So the positive terminal of the voltage source will appear here, and the negative terminal of the voltage source will appear to the anode of the diode. So this diode would actually will operate in the reverse bias. So here we can think of this diode will be in open circuit condition. So the voltage across this inductor L, if we consider this voltage across the inductor is VL, and the current passing through the inductor is my IL. So during that time, whenever this switch is on, what would be the voltage across the inductor? So during when the thyristor is on, you can see this terminal is connected to Vs and this terminal, it is connected to V0. So what would be the total voltage across the inductor?
Vs
Yes,
minus V0.
So this voltage, it should be equals to your, this voltage, it should be equals to Vs minus V0. Okay, in the last class, we also say at this time duration for which the transistor or switch will be turned on, it is D multiplied by Ts, and the time for which that transistor will be turned off, it is 1 minus D multiplied by Ts. So during that first half, when the transistor T1 is on, the voltage across the inductor is Vs minus V0. So we know my VL is nothing but L multiplied by Di over dt. So VL is nothing but the voltage across the inductor. So we can write Vs minus V0, and then it should be equals to L multiplied by. Now we are considering, since we are putting positive pulses across the inductor will charge up and the current through the inductor will increase. So we are considering the current change during that time. We are considering that del IL1, and the duration for time for this duration is what? D multiplied by Ts, right? And then we, from that one, we can derive our equation to be del IL1. It is nothing but Vs minus V0 over L multiplied by D into Ts. So we have already seen that in our last class, right? I am just recapping some of the concept we discussed in the last class. And during the negative half cycle, or when not the negative half cycle, during the time when that switch is not on, what will happen? So in mode 2, we consider our T1 is off. So whenever T1 is off, what will happen? This source voltage, this two terminal will be turned off. So the diode will be there. There should be inductor current, that is my plus minus VL. This is my L. And then we have a capacitor. And then we have a load. So this is my plus minus V0. This is my R. This is my C, and the current is flowing through this direction. That is my IL. So since this switch is off, so the input voltage, it will appear across the switch. So basically this portion will not have any contribution to what's happening after to the section right to the diode. So we can simply neglect this portion. So this is the circuit that will appear. But why this? We place this diode so that the inductor current will flow through this. It will go through the capacitor and the resistance and come back in this path, so that the diode can provide the path for the inductor to flow through, although the switched transistor T1 is in off state. So whenever this diode is operating, we can consider this diode to be an ideal one. So instead of this diode, actually, what we can do, we can just replace that diode with a simple short circuit. So circuit will look like this. So now, as you can see the positive terminal of the inductor is connected to the ground, but the negative of the terminal of the inductor is connected to the positive terminal of the output voltage. So the voltage across the inductor would be what?
Minus
B naught.
Minus B naught. So it will have a value that is my minus V naught. And similar way for the next half cycle also, when the switch is on, you will have a value that is Vs minus V naught. And whenever you have a negative value, so it will be minus V naught. Is there any confusion regarding the waveform we have drawn for the inductor output voltage?
Sir.
Any confusion?
Sir, I have a question, sir.
Won't
Yeah,
the
sure.
polarity be minus than plus?
Because we are considering the inductor voltage like this, the positive terminal here and the negative terminal here. But as you can see, when the T1 is off, the positive terminal is connected to the ground, and then the negative terminal actually it is connected to the positive terminal. So if you just write it down like this circuit will look like this. So suppose you have a inductor there. This is your positive terminal. This is your negative terminal. Now it is connected to the capacitor, and then it is connected to the load. So this is my plus minus V naught, and this is my VL. So the inductor current is in this direction, which is going through this. So as you can see, your VL polarity is exactly opposite of that of the output. That's why we are considering it minus V naught. You got my point? Any confusion?
Sir,
Yeah. Go
sir,
ahead.
why did we use short circuit instead of the diode? I still didn't understand that.
Okay, so diode actually, whenever your current is flowing through from anode to cathode, what will happen here? Diode will act like a simple switch, right?
Yes, sir.
Right? And what is the condition for the diode to operate? Your anode voltage should be greater than your cathode voltage, right?
Yes, sir.
So now, as you can see, if your diode is here, whenever the switch is off, your anode, this should be your anode and this should be your cathode, right? Your anode is connected to ground, which is in zero potential, but cathode is connected to plus of the, negative. So this voltage is actually, although we are considering it to be ideal one, so your cathode voltage is slightly will be in lesser voltage as compared to the anode because your current is going through in this direction, right? So it will simply act like a switch, ideal switch that doesn't have any potential drop requisite because we are considering, as of now, we are considering everything to be an ideal one. You got my point?
Yes, sir.
Is there any question?
Sir, sir, what changes the low-pass filter has made
Any
here?
question? I cannot hear you. I heard some sound, but I cannot hear anything.
So the low-pass filter, what changes it made here?
Sorry?
Shouldn't the low-pass filter, what changes it made here? Shouldn't the output be almost sinusoidal?
Output should be?
Almost sinusoidal, as we're
Why,
using a low-pass filter here.
why should we use a sinusoidal waveform? Because our input is DC and we want a DC output. So should we want the sinusoidal output or the DC one?
So we want a pulsating output.
Sorry?
We want a pulsating output.
Still, I didn't get you.
Sir, he asked that what's the function of the low pass filter here?
Okay, so this is my low pass filter, right? And before the low pass filter, when you have a switch, so output here between the terminal A and B, it would be a pulsating DC, right? Instead of a purely DC that the source is providing, right? So
Yes, sir.
if this is not purely DC, a pulsating one, so if you take the Fourier analysis, you will see a lot of X spectrum. There should be some DC X spectrum, then fundamental component, then third harmonics, then fifth harmonics, seventh harmonics, like that. So the purpose of this filter here is to erase all the higher frequency component that is available in the input, so that only the DC component, or sometimes on DC and the AC component, that should appear across the output V0. How it is doing that? So suppose you have an inductor and you have a capacitor. So the inductor value is what? XL value is what? 2 pi F multiplied by L. So as the frequency for the high frequency component, suppose this is fundamental, then third harmonics, then fifth harmonics, seventh harmonics, ninth harmonics, and zero harmonics. So whenever your frequency is zero, so this reactance would be zero, and the capacitor will be open one, because this is 1 over twice pi Fc. So as the frequency goes zero, this will provide a infinite path. So all the DC component that would simply go through the inductor to the output. But as soon as it gets the high frequency component, the more higher order it gets, with the increase of frequency, this impedance will be higher, right? And this impedance will provide a low path. So all the high frequency component, it will try to get suppressed by this inductor, but if it manages to pass through the inductor, this capacitor will provide a short path for the high frequency component, so that it can go through the capacitor rather going to the load. Make sense?
Yes, sir.
Yes, sir.
Any more question?
No, sir.
I hope you have studied filter, right?
Yes, sir, we have.
But I don't know why you don't have a clear concept of this one. Okay, no problem. So now during the time when your switch is off, then by doing the same math, we can say my current del IL2, it should be equals to minus V0 over L 1 minus D multiplied by TS, right? We have explained that how we got this current, so I am not going to derive that again. But as we can say, we have had two assumptions, right? The first assumption was what? My del IL should be 0 for switching time period, right?
Yes, sir.
And from that one, we concluded that my V lambda, D lambda over a switching time T, that should goes to 0, right? And the second assumption was my del VC should be 0. And from that one, we derive that my total current IC lambda D lambda over a switching time period, it should also should be 0 across the capacitor. So this equation is known as volt second balance. Balance. And this equation is known as ampere second balance. So simply, if you want to add these two equations, so by adding these two equations, we can simply write here. So I'm just taking this block here. So we can write del IL, that should be 0. So we can write del IL1 plus del IL2, that should, del I2, that should give you 0. And if you put your equation number 1 and 2 and try to solve for the relationship between output voltage and the input voltage, you will get your output voltage is equals to D multiplied by Vs. Similar way, if we do the volt second balance, so from volt second balance, what we get? So from volt second balance, what we can say? The voltage across the inductor during the time period T multiplied by Ts is what? Vs minus V naught, and the time period is T multiplied by Ts. And during the time when your switch is off, that is my 1 minus D multiplied by Ts, your voltage is minus V naught. So minus V naught multiplied by 1 minus D into Ts, it should be equals to 0. So if you simplify this equation also, you will get the same result. That is, your V naught is D multiplied by Vs. We have derived this equation in the last class, right?
Yes, sir.
So is there anything that I need to clarify? Otherwise, I will go into that waveform again, and then I will try to do the rest of the thing.
Sir, I think you can proceed.
So if you have any question, feel free to ask me, okay? Just a second, I am having trouble. Okay. So now, let me copy this thing. So okay, so okay. So that was my waveform, right? And in the previous slide, we just saw my output current for the time period del IL1. It was Vs minus V naught over L multiplied by D into TS. So the slope here, is it positive or negative?
Sir, positive.
Positive. So if we try to draw the output for the current here, so during the time when your inductor voltage is positive, so what will happen? Your inductor current will ramp up like this. Why is that? Because this voltage Vs minus V naught both are DC one. So this value and this value both are constant, right? So the current here will have a constant slope like this. Right? Is there any question regarding this?
No, sir.
Can you repeat this?
Yeah, so your source voltage and the output voltage both are DC, right? And the inductor that you are using in the circuit is also constant. You are not varying inductor, right? So this thing, the denominator and numerator, they both are constant. So you will have a constant slope. So just imagine like y equals to m multiplied by x. So this term here, it's a simple constant. It will have a simple constant slope, right? Right?
Yes, sir.
And during the negative half cycle, what will happen? We found that IL2, it is having a negative slope, that is minus V naught over L. Then we have 1 minus D multiplied by TS. So since we have a negative slope here, meaning that it will try to decrease from here, and after the end of the cycle, it will come where it is starting from. It has started from. Why is that? Because one of our assumption was my IL T plus T, it is equals to my IL T, right? Because we assume that in steady state, what our inductor current will be periodic, right? So similar way, when you will get always again a positive pulse here, the current through the inductor will charge up. Sorry. So the current through the inductor will charge up, and then again it will discharge like this. So the maximum point that we get and the minimum point that we get, we'll define it with a name. So the maximum point, we are considering it as IL max. And the minimum point we are getting, it is called IL min. And the total difference here it is known as del IL. Okay, somebody asked me for del IL1, what was the slope that makes this current ramp? So actually, this is the slope. This thing is the slope. And this is nothing but your time, right? T. And if you consider that with y equals to m multiplied by x, so this thing should be your slope. And since your Vs and V naught both are constant, and L is also constant in the circuit, so we can say it will have a constant slope. Now for the inductor, actually we are
Sir, I have
considering.
a question.
Any question?
Sir, why it's not starting from zero?
Why it is not starting from zero? Because we are considering it in the steady state value, right? So whenever you will start the circuit, it will start from zero, but actually what will happen? It will have a charging and discharging period, and then finally after some point, it will reach to its steady state value. Okay. So we are considering about this portion, not the initial part of the portion. Okay.
Yes, sir.
So for every circuit, there should be some cycle for which you will get the output variable, right? And after some cycle, the circuit will reach its steady state. So we are considering about the steady state portion, not the initial couple of portion when there will be lots of transients. Okay. So
Okay.
this average current, we are considering it IL. So the total difference between IL mean and IL max, we are considering it del IL. So if you want to draw, get the equation of IL max, so what we can write, IL max is what? Your average value IL. Then with that, if you add with this one, if you add this magnitude, then you will get IL max, right? What is this magnitude? This magnitude should be half of this total magnitude. So we can write plus del IL over 2. So del IL, actually this positive slope and the negative slope, this time this is half of the total length. So you can either choose the positive slope one or the negative slope one. In your book, they have chosen the negative slope one. So I am just going with the book. But if you consider the positive or the charging slope here, the magnitude, it will give you also the same value. So now here, one thing I need to tell you first is that, okay, here another thing, okay. So my actual circuit here, if you see my actual circuit, like this. So output here, V naught, with the introduction of the low pass filter, this output here, it will be purely DC, right? Or very close to this one. So if this voltage is DC, and then we have a resistive load, so the current through the load, it will be a DC one, right? And whatever the average value of this inductor current, IL, and the current, DC current that is going to the load, that is I naught, these two current will be equal. So in that case, we can say my IL, the average value of the inductor current, is equals to the average current that is going to the load, which is nothing but my V naught over R. So if I put this value here, so we get V naught over R plus, if you take the magnitude of it, so you will get V naught over L, 1 minus D multiplied by TS. So TS is nothing but 1 over Fs. So if we take V naught common, then we get 1 over R plus 1 over L Fs. Instead of Ts, we are considering Fs. Then it can be written as 1 minus D. That is the equation for IL max. Any question?
So can you
Sir.
repeat why
Please
IL is equal
repeat,
to I
please.
naught?
Sorry?
Sir,
Sir,
can you
repeat,
repeat
please.
why IL is equal to I naught?
Yeah, because here your output was pulsating DC, right? But after introduction of the low pass filter L and C, the output here, it will be almost purely DC, right? So if your output is DC, if you are putting this DC across a resistive load, so the current through the load, it should be a DC value, right? Which is nothing but V naught over R, right?
Yes, sir.
Sir, why are we not considering current through capacitor?
We will be considering that. Just give me 1 more minute, okay? Let me derive the equation for IL max and IL min, then I will show you how the capacitor currents are varying, okay?
All right, sir.
So similar way, if you want to get the minimum value of IL min, here, what you can do, your IL min is nothing but IL minus del IL over 2. So again, we can write V naught over 1 over R minus L multiplied by Fs 1 minus T. Similar equation, right? So now, let me talk to you about the effect of inductance on that current waveform. So suppose we have considered the inductance such a way that our inductance current through the inductance is varying like this. It is varying like this. But if you decrease the value of the inductance, what will happen to the inductor current? So if you decrease the inductor current, the current will go downwards. Again, if you decrease the value of the inductance, it will go more downwards until it has a minimum value of inductance for which you will have a zero starting current for each and every switching cycle. If you further decrease the value of the inductance, then what will happen? The inductor current will look like this. So it will go further lower value, then it will reach to 0, and then it will start to stay in 0 for some times. And then again, it will start to charge, and then it will goes to 0, and there will be no current for some period. So this mode where your current goes to 0 and there is no current for a certain period of time, this is called discontinuous mode. But at least when the current is starting from 0, it is charging up and then going back to 0, and then again, without delaying any time, it is again charging from 0 to some specific value. We can still consider that to be a continuous current mode. So all these things that we have discussed, except the red one, it is actually the continuous mode current. So what will be the extreme point for the continuous current? Can anyone tell me?
স্যার এমন একটা পয়েন্ট যেখানে জাস্ট ওই কার্ভটা টাচ করবে বাট স্টে করবে না।
That means your IL main, it should be equals to 0, right? Not negative.
Yes, sir.
Yes.
Right?
Yes, sir.
So if your IL mean becomes 0, that means this thing we can write V naught over 1 by R multiplied minus 1 over L mean. We are considering this inductance to be the minimum inductance. multiplied by Fs, 1 minus D, that value should be equals to 0, right? So that gives you L mean is nothing but 1 over R multiplied by Fs multiplied by 1 by D. So this is the minimum amount of inductance that you should put in the circuit so that you have a continuous current to the inductor. If you put the inductor value less than that, then what will happen? The current will enter into the discontinuous mode. So actually what you need to do, you have to put the inductance value higher than this L min value. You got my point?
Yes, sir.
Sir, in the equation of IL max and IL min, shouldn't the value be 1 by twice L?
Sorry, yeah, it should be half. It should be half, right? So
Yes,
it
sir.
should be half. So actually what is happening, 2 will appear here, right?
Yes, sir.
Thank you for that one. So now what is happening here is that, so we got the value of the inductance for which we have to make sure that you should have at least the inductance value that is higher than this L min value. Now what is happening? So in your circuit, you have an inductor, then you have a capacitor, then you have a load. Okay, so inductor, you have a capacitor, and then you have a load, that is my plus minus R. So as I said before, this V naught is a constant DC, meaning the current that is going to the load I naught, it is constant as well. And from the waveform, we are seeing that your inductor current will have a constant value. So this waveform, actually you can think of two waveform. One is the DC one and one is the DC value like this. And if you superimpose a AC current on top of that one, so these two will add up to get this waveform, right?
Yes, sir.
So actually the DC value that you are getting here, it is actually going to the where? It is going to the load, right? So
Yes, sir.
all the hiccups or the changing current that is going to the inductor, where it will go through? It will go through the capacitor, right?
Yes, sir.
So we can write here, suppose in a Kirchhoff's current law equation, we can write IL is nothing but your IC plus I naught, right? So we can write del of IL is equals to del of IC plus del of I naught, but practically this current is constant. So whatever the value of the inductor current changing, this current should go through the capacitor value, right?
Yes, sir.
Is there any question? Any question? So if you draw the waveform for the capacitor voltage or capacitor current, we'll find that it will have a waveform like this. So this is your capacitor current. In the last class, we have also got the example, like suppose this is my 50 amps the maximum value that we got here is 55 amps, and the minimum value that we got here is 45 amps. So this is minus 5 amps, and this is plus 5 amps. So what is happening here? When the inductor value, this inductor current average value is equals to the current that is going to the load, right? And this current is always constant. Suppose this is 50 amps. So what is happening here? Whenever your inductor current is 45 amps, what is happening here? 5 amps is going in the opposite direction. That's why this is negative. To make this current 50 amps, right? But whenever your inductor current is above of this average value, then the difference here, suppose this is 55 and your current is 5 amps. So then you can have 5 amps current in this direction, which is your positive current. You got my point, right?
Yes, sir.
Any question?
No, sir.
So if you have any question, just ask me, okay? If you write it down in that message, sometimes I cannot see that one. So now, if this is your capacitor waveform, then your capacitor current is what? You know what is the value of the capacitance in your circuit? C is nothing but Q over V, right?
Yes, sir.
So we can write my del Q is nothing but C multiplied by del V, right?
Yes, sir.
So as you can see, so my Q is nothing but, what is Q? It is integration of current, right? Because your I is nothing but dq over dt, right? You know this equation, right?
Yes, sir. Yes, sir.
So now, as you can see, we said the difference between my minimum value and the maximum value is del IL, right? And this del IL is this thing, right? So from here to here, it is also my del IL, right? Which is we got from here, right?
Yes, sir. Yes.
Right?
Yes, sir.
So what is this value? This value should be
Del IL by 2.
IL over 2, right? This total time is my D multiplied by TS. So if this is the total half of it, so the time from here to here, it should be half into D multiplied by TS, right?
Yes, sir.
Similarly, the time here to here, this point, it should be 1 minus D divided by 2 into TS, right? So if we consider this A and B, so what is should be the length of AB? AB should be what? Half into D multiplied by TS plus half into 1 minus D multiplied by TS. So that gives you half multiplied by TS, right?
Yes, sir.
So now, so if we want to get the total charge, this is current, right? And if you take the integration, you will get the charge, right? So integration means what? The getting area under the curve, right? So suppose this is ABC. So what should be the area of triangle ABC? So your del Q is nothing but the area of the triangle ABC, right? Which is nothing but half multiplied by this length, which is half multiplied by TS multiplied by the height. Height is what? Del IL over 2, right?
Yes, sir.
So it should be my del Q, it should be 1 over 8 multiplied by TS multiplied by del IL. So for del IL also, we are considering this negative slope portion because your book considered that one. You can also take the positive half portion. It will give you the same answer. So this should be V naught over L multiplied by 1 minus D multiplied by TS. So your del Q is nothing but 1 over 8 multiplied by V naught over L 1 minus D multiplied by TS square. And then this del Q is nothing but C multiplied by del V, right? From here, we can write it down, right?
Yes, sir.
So what should be the value of C? So C value should be 1 over 8 multiplied by V naught over del V multiplied by 1 by L, 1 minus D. And instead of this TS square, we can write it as Fs whole square, right? This should be the value of. So if you consider a constant inductance, constant frequency, and constant duty cycle, for a constant output, if you decrease the value of del V, what will happen to what you need to do in the capacitor value?
Sir, could you repeat the question?
So this is the value of C, right? We got
Yes,
from
sir.
the equation, right? So let me write this equation in a different manner. So del V is what? 1 over 8 multiplied by V naught over LC Fs square 1 minus D, right?
Yes, sir.
So suppose your output is constant, your L is constant, you are switching frequency is constant, and your D is constant. So in order to keep the ripple of the output voltage, what you need to do?
Sir, increase the capacitance.
Increase the capacitance. So what you need to do in order to avoid the ripple in the output voltage, we'll make sure that the capacitor value is so high that this ripple will become very small, so that the output voltage at the load, it will have very less ripple, or in other words, we can say output voltage would be purely DC. Make sense?
Yes, sir.
Any question? Any question? So we have studied almost 1 hour. So can I get another half an hour? Are you feeling bored?
No, sir. Sir, can you please scroll a little bit upwards?
I will give that PDF to you in the classroom. So don't worry about this, okay?
Sir, sir, can you please repeat why did we take del I not equal to 0? It's in the left side of the screen.
Okay, what we said that suppose you have a current like this. So if you decrease the value, what will happen? This current will be shifted downwards. Okay. And if you further keep the L value lesser, then what will happen? This current will come like this. So now this is your IL max, right? This is your IL mean, right?
Yes, sir. Now I understood, sir.
So what is the crucial point for IL to be? It should be 0, right? Before it can enter into the discontinuous mode, right?
Yes, sir.
So if we consider this critical point, and then if we choose the L in such a way that we will always keep the L higher than this value, then we'll make sure that the current through the inductor will be a continuous current rather than it is discontinuous one. Make sense?
Yes, sir. So is it possible that the curve goes a little bit downward so the current becomes negative? I mean, is it possible?
No, the current will never go to negative. Why is that? So suppose this is your actual circuit, right? Suppose this is your actual circuit. Let me draw it. So during when this switch is on, what is happening here? Current through the transistor T1, it is going to the inductor and then it is dividing here and come back through the to the source, right?
Yes, sir.
Right?
Yes, sir.
But when your switch is off, then what is happening? So your switch is off, meaning all the inductor current now, because inductor doesn't like the current direction to change, so it will go through this resistance, and then it cannot move through this direction because this thing is open circuited. So it will go through the diode in this direction as much time as it gets, because this current, how much time it will flow, it will be dependent on the value of L, C, and R, right?
Okay, sir. Yes.
So if it needs to go in the backward direction, that is in this direction, is there any way that
Okay.
it can go? Because this diode will not operate and this transistor is already off, right?
Yes, sir.
So there is nothing to support this flow of current in this direction, right?
Sir, if we if we add reverse polarity, then the current will flow backwards.
Reverse polarity means?
মানে স্যার যে ভিএস এর যে পোলারিটি স্যার -2 প্লাস এটাকে যদি রিভার্স করে দিই সেক্ষেত্রে
Yeah, but still, if you do that like this, so if you do that, your switch is open, right? So if this is open, no matter whether this polarity is in this direction or this direction, the inductor will never have a path to go through in the opposite direction, right?
জি স্যার
Because this thing is off, right?
Sir, the current through the capacitor is still flowing.
The current through the capacitor,
Yeah, the current is also entering. I mean, in this case scenario,
Mhm.
you earlier said that um, the current through the
Sir,
capacitor would be zero.
sir,
I said that the average current, if you do the integration of the current with respect to time for a one switching period, it should be equals to 0, right?
Yes.
So if you see that triangle, whatever have the positive value, they will have the exact negative value, right? So if you sum them up for the entire one time period cycle, you will get this value to be 0, right?
Yes, sir. Yes, sir.
Any question?
No.
So now, can I have one half an hour more so that I can show something new to you, because I have already shown you what I have discussed in the last class, right? So there is nothing new.
Yes, sir. But I think if you start something new, no one will follow you.
Why is that? It's already 1 hour. Okay, so I will not start something new today, but what I will try to do is that, so the inductor current, so I will just wrap up this buck converter for you. So suppose now this is the maximum inductor current, right?
Yes, sir.
So the maximum inductor current is happening whenever this switch is on, right? T1 is on, right?
Yes, sir.
So what should be the current rating of the transistor T1? What should be the current rating of T1? It should be at least IL max, right? Because this amount of current, it should be going through the transistor to the inductance when T1 is on, right? So IL max should be the current that should go through the inductor. What should be the value of diode peak inverse voltage? So when this switch is on, or we can say this circuit, so whenever this switch is on, the diode will be turned off, right? Because it is in open bias, reverse bias position.
Yes, sir.
So what should be the reverse bias across the inductor? Across the diode? It should be the same as the source voltage, right?
Yes, sir.
So what should be the peak inverse voltage for the diode?
Sir, VS.
It should be Vs, right? So now I will take 5 more minutes, and then I will conclude this lecture as for today. Tomorrow we will discuss about the boost converter, and we will try to do some math regarding the buck and boost converter. So for the buck converter, actually what is happening here is that So we have a switch here. Then we have a diode. Then inductance. Then capacitor. Then resistor. So this is my V naught. This is my R. This is Vs. So all the thing in between it is known as buck converter or step down converter. Why is that? Because whatever voltage you are giving here, your output voltage is nothing but D multiplied by Vs, and where we are considering D to be less than 1. So, can you see, if we consider this transistor to be an ideal one, the diode to be an ideal one, then the inductor and capacitor, is there anything in that circuit within the buck converter that can consume power?
No, sir.
Meaning that if this is my input current I in and this is my output current I naught, so the input power P in, it should be equals to Vs multiplies by I in, right? And
Yes,
your
sir.
output power P output, it should be equals to V naught multiplied by I naught, right? Because we are considering everything that is ideal and lossless within the buck converter. So safely we can say whatever power you are dumping inside the circuit, it will come across the load, right? So we can write our P in, it should be equals to my P out, right? So Vs multiplied by I in, that should be equals to V naught multiplied by I naught. Or we can write Vs multiplied by I in, that should be equals to V multiplied by Vs multiplied by I naught. Or if we cancel Vs, then we can write your I naught is nothing but 1 over T multiplied by I in. So, in a magnitude or ratio, how much we are stepping down the voltage at the output, the current will be increased in that amount so that the power will remain same as the input. You got my point, right?
Yes, sir.
So that's why this DC to DC converter, actually the buck converter or boost converter, it DC to DC converter, it is also known as, if it is V in, this is your I in. Similarly, if it is your V out and this is your I out, it is, this DC to DC converter is also known as DC to DC transform, because they do the exact same thing as transformer does for the AC voltage and AC current. You got my point, right?
Yes, sir.
So the last thing I will conclude here, that suppose what is happening here is that, okay, so that's all for today, because if I say something now, you will forget that for tomorrow. So for tomorrow, we'll start from what time?
Sir, you mentioned 7 p.m.
Is that okay for you all?
স্যার 8:30 হলে ভালো হয় স্যার, 8টার সময় নামাজ আছে তো।
6:30?
স্যার 8টা।
Is that okay for everyone? Is that okay for everyone?
Yes, sir. 8:30 is okay.
স্যার
Or
7টায় হলে তো ভালো হয়।
Okay, then 7. From 7 to 8:30. Because tomorrow we'll go through a lots of new topic. So at least I need 1.5 hour to discuss all these things, okay? So tomorrow, make sure I get 1.5 hour for the lecture. So if there is any last moment question, anything? Nothing? So then you are good to go, except the CRs. CR, I need to talk to you. Other than that, everybody can leave.
Assalamu alaikum.